Hi, my name is John Schultz, and I'm with Compass Technology. Today, we're going to do some material measurements at E-band. To do that, we're going to use a focus beam system built by Compass, combined with a fancy vector network analyzer system and frequency extenders built by Calibration Technologies. Our focus beam system right here includes two lenses. These lenses are the focusing elements that take energy and make a nice spot at our focal point, which is where we place our sample. These lenses are made from Rexolite. On the other side of these lenses, you'll see our frequency extenders. These frequency extenders operate from 60 to 90 gigahertz. You'll also see that they have horn antennas on them. And so they feed the lenses, and they're spaced so that the lens focuses the energy right at the sample position. Now you'll notice on our sample holder, our frame, we have it on a turntable here. Today, we're going to just do measurements at normal incidence, but if we wanted to, we could rotate this in an automated way and take data at other angles. Similarly, with our frequency extenders, you'll see that they have rotation stages and linear stages as well. And we have those on there because we need to exactly tune the position of these extenders and the horns so that they align with the lenses and so that we get everything nice and symmetrical at the center. So these extenders also have wires coming out of the back of them. These are RF, low frequency RF and control cables, which then talk to a Cobalt vector network analyzer, which you see here. This Cobalt VNA is a high-end desktop system, and it talks to our computer via USB, and we control it so that we can then take data from 60 to 90 in even frequency steps. And so these will operate the frequency extenders and allow us to take data. So let's go ahead and do some material measurements. Today, what we're going to measure is some undoped silicon. Undoped silicon is low loss, and so we expect an imaginary part of the permittivity to be pretty close to zero. It is also a relatively high dielectric constant, so the real permittivity will be somewhere between 11 and 12. Before we do our measurement, we have to calibrate. Calibration is measuring the system by itself with no sample loaded. Let me go ahead and press the button here. So when I press the button, that then talks to the vector network analyzer, and the VNA, in conjunction with the frequency extenders, essentially scan in multiple steps from 60 to 90 gigahertz. And it collects data at each frequency. And so we have a number of different frequencies we characterized here. And you'll see there's a trace now on our software that shows the insertion loss of this system. It includes both just the insertion loss of the lenses and the space loss and so forth, and also really just the way the analyzer and frequency extenders were set up. All right, once we have a calibration measurement, we can take our sample. So here's the undoped silicon. You can see it's just a shiny, clean wafer. And we're going to tape it in place here in the sample position. So I'm placing it at the focus. And our focus in this case is confined to the middle of the sample. At these frequencies, our spot size, half power spot size, is on the order of half an inch or so, about a centimeter and a half. And so we don't illuminate the edges at all, really. All right, so I'm going to do the same thing. I'm going to press the measure button here. You can see in our software, I've already put in a description for silicon. So we're going to click measure, and we're doing the same thing. We're measuring each of the same frequencies that we measured for our clear site. And then we're doing a response calibration. We ratio the measured sample to the clear site. There's a second thing that we're doing as well. We're doing time domain gating. So you'll see right here, there's a time domain gate input. In our case, we have it set at 1 nanosecond. The speed of light is such that 1 nanosecond corresponds to about 30 centimeters or so of travel. And so that puts essentially a window around our specimen, just like this. And that allows us to zero out any sort of reflections and multipath from the discontinuities of the lens, the horn, and internal to the network analyzer and the extenders as well. Okay, so now you can see the amplitude in dB of the insertion loss or transmission coefficient of our sample. And you can see it's a squiggly line. This is sort of a sine wave curve. And that sine wave shape has a peak that's really close to 0 dB. And then it has, it'll probably, reach a minima here, maybe right around or just above 90 gigahertz. And those peaks and minima are due to constructive and destructive interference between the front and the back surface of our silicon slab. And they interfere, constructively and destructively to either give you lots of transmission or very little transmission. In this case, we dip down to about 4.5 or so dB as the insertion loss. We also record phase in addition to amplitude. And here you can see the phase delay. If I was just measuring air, our phase would be at 0 degrees. But because we have a material that has a higher dielectric constant, it slows down the energy going through it. And so that results in this phase delay that we see here that varies from about 100 degrees or more, depending on frequency. All right, so from that phase and amplitude data, we can go ahead and compute the real and imaginary permittivity. So in our software, I'll scroll down here to our process tab. In this case, you have to input the thickness. And we know that our specimen is 26 thousandths of an inch. And then we're going to give our solver a guess value. It doesn't have to be close. It has to be somewhere in the neighborhood. In this case, we're going to assume a permittivity around 10, and that just gives us a starting point for searching for the actual correct answer. I'm going to click on the permittivity button, and it'll go ahead and solve for the exact permittivity based on our measurement data. And you can see it's pretty quick. In our case, you can see a solid line, and that is the real part of the permittivity. And the real part of the permittivity of the silicon is about 11.7-ish, give or take, which is pretty much what we expect for undoped silicon. And then there's a second line here, this dashed line. This is the imaginary part of the permittivity. You can see it's pretty close to 0 and wiggles right around 0. So in this case, it's a very low loss sample, and we have very little loss, and therefore the imaginary part of the permittivity, or the loss, is pretty much close to 0. So that is measurements of a simple dielectric material with our focused beam system. Thanks for watching. If you want more information on dielectric measurements, whether with the focused beam or any other of our devices, you can check us out at compassTech.com. If you want more information on the vector network analyzers or these frequency extenders from Copper Mountain, you can check them out at coppermountaintech.com. Thank you.